Welcome back. Now we move to another important class of stochastic processes known as Poisson processes. A Poisson process is a model for counting the number of random events that happen during a time interval. Here, unlike the previous chapters, time is continuous. So a Poisson process is usually denoted by n sub t or n of t for t positive. So it's a collection of random variables. So for each t, n of t is a random variable that takes integer values. Okay. So for example, n of t may represent the number of visitors to a museum during the interval 0t. Okay. So it's a cumulative way of counting. Okay. So when t increases, n of t increases, but not necessarily strictly. It may model the number of clients that arrive to a bank or post office during the time interval 0t, or the number of cars passing by a certain location in a road during the time interval 0t. For an insurance company, it may model the number of sinisters or accidents that happen during the interval 0t. Okay, so there are two types of Poisson processes, homogeneous and non-homogeneous. In this video, you are going to cover homogeneous Poisson processes. So when we want to make a mathematical model for a random situation, it's not enough to say that it's just random. We have to say what kind of random it is. Okay, if we want to compute probabilities, we have to specify the distribution of the process or the random variables. So a stochastic process n of t is called a homogeneous Poisson process with intensity lambda. So lambda is a parameter in this case, and we'll explain what is the significance of lambda shortly. If three conditions hold. First condition is just a normalization condition. It says that n of 0 is 0. So basically it means that at time 0, no one is there. If you think of n of t as counting the number of arrivals or jumps, if you like. And the second condition is technical a little bit, but it's very useful to prove theorems. It's an independence condition. So it tells that for every increasing sequence, t1, t2, tn of times, this collection of random variables, n of t1, or n of t1 minus n of 0, because it's 0. This is the first random variable. The next random variable is n of at time t2 minus n at time t1, etc., up to n of tn minus n of tn minus 1. So all this collection of random variables is independent. Okay. So otherwise stated, what happens during the interval, the time interval tn minus 1 tn, is independent on the past. So we say that n has independent increments. And the most important property is the property giving the distribution of the process. It tells us that for every 2 times s and t non-negative, the difference between n of s plus t and n of s follows a Poisson Poisson distribution of parameter lambda t. Okay, so what does this mean? It means that, as you know from first course on probability, the probability that this random variable takes the value k is given by lambda t to the k over k factorial times e minus lambda t. This is the definition of a Poisson distribution. Okay, so note here that homogeneity actually means here that the distribution does not depend on s. So it only depends on the length of the interval, which is t in this case. Okay. The next video, we shall remove this restriction, and then we'll get non-homogeneous Poisson process. Okay, so what is the significance of this? This is just the number of, if you think of n of t as counting the number of clients or arrivals or cars, this is just the number of clients arriving during the time interval ss plus t. Okay, so it's an integer valued random variable. So it takes all the values k from 0 to infinity. Okay, so in particular, if we put t equal 1 here, then the n of s plus 1 minus n of s follows a Poisson distribution of parameter lambda, okay, because we put t equal 1. Okay. So in particular, the mean value or the expected value of this number is just lambda. So therefore, lambda is the average number of arrivals or jumps during an interval of length 1. Okay. This is the significance of the intensity. Okay. So if lambda is small, it means that few clients arrive. If lambda is big, it means that a lot of clients arrive. So this is the first remark. Second remark, well, let us see what happens during a small interval of time of length h. So in particular, since n of h follows a Poisson distribution of parameter lambda h, then the probability that n of h is 0 is precisely exponential of minus lambda h. Okay. And the probability that n of h takes the value 1 is lambda h e minus lambda h, because this corresponds to the value k equal 1. Okay. And if you compute the probability that n of h is at least 2, then you can write it in two ways, actually. You can write it as lambda h squared over 2 factorial e minus lambda h plus etc. So it's an infinite series. So, but it's of order big O of h squared, okay, because it starts with lambda square h squared over 2. Okay. Why this is important? Because if we take the second equation here, if we divide by h and let h tends to 0, this ratio tends to lambda. And here, when we divide by h and let h tend to 0, the limit is 0 because it's a big O of h. So the first limit tells us that we can think of lambda as being the intensity or the speed of arrivals or jumps during a small interval of time. And the next limit tells us that the probability of more than one arrival in a small interval of time is negligible, it tends to 0. So it means that clients or events happen once at a time. Okay, so we don't have two customers arriving at the same time. Okay, so this, of course, is a simplifying assumption. Okay, so let us give now an example of computing probabilities related to a Poisson process. So let us assume that the car accidents of a certain driver happen according to a Poisson process with intensity 0.01 per month. So it means that on average, the driver makes one accident every 100 months. So it's a low probability. So the first question, we have to compute the probability that the driver has no accident during the first year. Second question, we have to compute the probability of exactly one accident during his third year of driving. And in the last question, we have to compute the probability of at least 2 accidents before the end of the second year, given that there was exactly one accident during the first year. So it's a conditional probability. So as you shall see, this is very easy actually because of our assumptions. So what is the probability that there's no accident during the first year? So since here we are counting per month, so 1 year is 12 months. So the event that there's no accident during the first years means precisely that n of 12 is 0. And the probability of this event, by definition, this is just, as we said before, e minus lambda times the length of the interval, which is 12. So it's e to the minus 0.001 times 12, which is about 0.88. So it's a high probability, okay, because it's a good driver. Because the intensity is small, so the probability of no accident is high. Okay, next probability, exactly one accident during the third year. So the third year is the time between month 24 and month 36, okay, because 2 years, 3 years. So we have to compute this probability of n of 36 minus n of 24 equal to 1. So there's one accident during the third year. And now, since it's a homogeneous Poisson process, it doesn't depend. It depends only on the length of the interval, which is 36 minus 24, which is 12. So it's the probability of n of 12 equal 1, and this is easily computed as lambda times the length length of the interval. So lambda h e minus lambda h, or lambda t e minus lambda t, corresponds to k equal 1. So it's we get a low probability actually. Okay, so around 10%. Now the last question is a conditional probability. So at least 2 accidents before the end of the second year. Okay, so or during the first 2 years. So we have to compute the conditional probability given that there is exactly 1 accident during the first year, so n of 12 equal 1. This is the event on which we are conditioning. And the event for that we want to compute the probability is n of 24 is at least 2. Okay. Now, since n of 12 is 1, this is equivalent. So n of 24 is at least 2 means that n of 24 minus 1 is bigger than 1, but 1 is n of 12. So we have to write it in this way because we can compute probability of events of this form. Okay. But now we use the independence assumption. So what happens during the interval 12-24 is independent on the past. So we can get rid of this conditional. Okay. But so this is the probability of n of 24 minus n of 12 is at least 1. And once again, this depends on the length of the interval, which is 24 minus 12, which is 12. Okay. And this is actually, we can compute this in 2 ways, as you probably know from the first course on probability. The best way to compute this is to write this event as the complement of the event that there's no accidents during the first year, okay? Because these 2 events are complementary. So it's 1 minus the probability. The second way is to write this as an infinite series. Okay, so this is the probability of n of 12 equal 1 plus the probability of n of 12 equal 2 plus etc. So if you want to write it in this way, you'll get an infinite series, but then when you simplify, you'll get exactly the same result. So try to do it in another more complicated way. So, but you already computed this in part A. So this is 1 minus 0.8869, and this is about 11.3%. Okay. So this is a typical question, very easy, that you can ask in the exam. Okay, now let us dig a little bit deeper into the properties of a Poisson process. So, as you said, a Poisson process counts the number of arrivals or jumps or events that happen during a time interval. So now we want to ask clients or accidents happen at certain random times. Okay, so here we'll have to distinguish between 2 times: the arrival times or the jump times and the inter-arrival. So the first arrival or first jump, or first event if you like, happens at a certain random time, capital T sub 1. And the next event happen, we have to wait T2, a random time T2, okay, before the second arrival happens. Okay. So in general, what we'll denote by Tn the time arrivals between the n minus first arrival or event and the nth arrival. Okay. So here you have to be careful about distinguishing between 2 random times. Okay. So Tn and Sn. Okay. So the arrival times will be denoted by Sn. So if you like, you can draw a picture, if you like, in axis. So first arrival time, it coincides actually with, so T1 equal S1 in this case. Okay. And then the next event happens at time S2. And S2 minus S1 is precisely T2. Okay. So Sn are the arrival times and Tn are the inter-arrival times. Okay. So they model the duration or the time difference between 2 arrivals. Okay. But of course, as you said, S1 equal T1 in this case, because we can write S minus 1 equal 0, if you like. Okay. So the question is, how are the inter-arrival times distributed? And the answer is that the inter-arrival times Tn are independent and follow an exponential distribution with the same intensity lambda, with the same parameter lambda. Okay? And this is very important because it helps us simulate Poisson processes. Okay, so therefore Sn is an independent sum of exponentially distributed random variables. Okay. The proof is not difficult, so let us consider first the distribution of T sub 1, which is S1. So what is the event that T1 is at least T, or strictly greater than T? It means that there's no arrival during the interval 0t. Okay, so the first arrival time happens after time small t. So it means on the interval 0t there was no event or no jumps or no. Okay. So the event T1, capital T1 bigger than t is the same event capital N of t is 0. And now we can compute the probability of this event. This is just E minus lambda t, as you know by definition. Okay. So this means that T1 follows an exponential distribution of parameter lambda. So if you like, you can write this equation in another way. You can write it as P of T1 less or equal than T as 1 minus E minus lambda T, and this is the cumulative distribution function of the exponential. But they are equivalent. So you can take this as a definition of an exponential random variable. Okay. So T1 is exponentially distributed with the same parameter lambda. Now, what about T2? Okay, so let us condition on the event T1 happens at a certain time S. So what is the condition probability that T2 is strictly bigger than T, the inter-arrival time? So the duration between the first arrival and the second arrival is at least T. Okay, so giving that T1 equal S. So it means that on the interval S plus T, there was no event or no arrival. Okay, because we have to wait at least an amount small t of time before we get the second arrival. And by the second condition of independence, the number of jumps or the number of events happening during this interval follows a Poisson distribution of parameter lambda t. This is condition 3 actually, and is independent on the past. So here we are using assumptions 2 and 3 of the definition. Okay, so therefore we can get rid of this conditional event. So the probability of T2 bigger than T is the same as the conditional probability. And it's the probability of no arrival during the interval S plus T of length T. And this is precisely E minus lambda T. So once again, T2 is independent on T1 and follows an exponential distribution with parameter lambda. Okay. And we can continue in this way. If we compute the condition probability that T3 is at least small t, and T1 equal S1, T2 equal S2, then this is the same thing as, so we have to wait at least t time before the next event. So this is the probability of no arrival on the interval S2 plus t, given the past. But the independence condition tells me that we can get rid of the past because it's independent on the past. And the probability of no arrival during this interval is the same thing. It's E minus lambda t. So once again, the T3 is independent on T1 and T2 and follows a Poisson distribution of parameter lambda. And if you continue in this way, we get the result. Okay, so T2 is independent on T1, T3 is independent on T1, T2, and so on. Okay, so not terribly difficult. Okay, so therefore, this result permits us to write an algorithm for simulating a Poisson process of intensity lambda, homogeneous, of course. But so I'll present two algorithms, one giving the number, a prescribed number of events or jumps, that I call it n. Okay, so we choose a positive integer n. Okay, for example, you want to simulate a Poisson process for, let us say, 10 arrivals. Okay, so have 10 jumps if you like. Okay, then we set S of 0 equals 0, and then we do a loop. We generate an exponential distribution E with parameter lambda, and we set S of k plus 1 equal Sk plus C. So E is the inter-arrival time, and Sk are the arrival times. Okay, so here we are simulating the arrival times. And at the end, we return the vector S of arrival times and the vector giving the values of the Poisson process that are from 0 to n minus 1. Okay, because we have n jumps. Okay. Okay, we can return actually 0 from 0 to n if you like, but it doesn't really matter. We'll implement it actually in a later video. Now, if there is another way, there is another problem. So unlike the previous algorithm, we can provide a second algorithm where we want to simulate a sample path of a Poisson process on a prescribed interval 0t that I called capital TF, final time. Okay, so unlike the previous algorithm, the previous algorithms we gave the number of jumps. Here we don't know what is the number of jumps in advance, but we know the final time. So we want to simulate a Poisson process on a finite interval 0t, TF. So the algorithm is the same. So we first initialize our variables s of 0 equals 0 and x, I denoted it by capital X. So x is the Poisson process actually. So, and we do a loop. As long as the arrival times are not bigger than the final time, we do the same thing. We generate an exponential random variable, and we do the same thing. We add to sk the inter-arrival time, and we increment the Poisson process by 1, okay, because it's a counting process. And we increment k, of course, and if n is the last value of k, so that ends the loop, then we set Sn equal to f and we delete xn, and finally we return two vectors, the vectors of arrival times s and the Poisson process x. Okay. So note that x takes integer values, but s can take any positive value. Okay. So, but both are random. So we'll implement this in a later video. And now I will end with a useful result about the sum of two independent Poisson processes. If we have two Poisson processes, capital N1 and capital N2, with intensities lambda 1 and lambda 2, so both are homogeneous, and we consider the process which is their sum, so capital N is 1. What can we say about the sum of these two processes? The answer is that the sum is also a Poisson process, and its intensity is the sum of the intensities. You can try to prove that if you want, but it has some useful applications in the insurance industry. If you have an insurance company having two branches, an automobile branch and a habitation branch. So as we said, we can model the number of cylinders in the car branch by a Poisson process of intensity lambda A, and the number of cylinders in the habitation branch by another independent Poisson process of intensity lambda H. Then the total number of cylinders of the company is modeled by a Poisson process of intensity lambda A plus lambda H. And next example, so we have again an insurance company, and we can model the number of cylinders for each policyholder by a Poisson process of intensity lambda. But if we have n policyholders, then the total number of cylinders can be modeled by a Poisson process of intensity n times lambda. So it's lambda plus lambda plus lambda plus lambda n times. Okay. So this concludes section 3.1 on the homogeneous Poisson processes. And in the next video, we are going to cover non-homogeneous Poisson processes. So thank you for your attention and see you next time.